So for our second feature today, we'll have Dor Elboim from Princeton who will tell us about critical one-dimensional multi-particle DLA. So please.
Yes. Thank you, Ohad. Thanks for inviting me, and thank you all for coming. So yeah, I'm going to talk about multi-particle DLA. Yeah, this is a joint work with Danny Nam and Ellen Sly. Okay. So let's talk a little bit about the regular diffusion limited aggregation, or DLA. So this is a class of models in which every time you have one particle coming from infinity by a random walk and joins a growing aggregate. And you study this aggregate, how it is growing, what is the shape, what is the rate of growth. And yeah, there are some conjectures about limiting fractal behavior, but not a lot of results are rigorously known. Yeah, we will talk about a variant of this problem, which is the multi-particle DLA. So here, the only difference is that all the particles move simultaneously, which means that you have a sea of particles and they are all moving simultaneously and independently. And again, you have a growing aggregate like that. And here is a picture. Okay, yeah, let me define the model more accurately. So the model is defined in dimension D, and you have a parameter of the model, which is the particle density, lambda. What is the aggregate? The aggregate will just be a set of vertices of the grid that is growing with time. And it starts from just being the origin, from containing the origin. Okay, so initially on each one of the vertices, you will have Poisson lambda particles. So on average lambda particles on each one of the vertices of ZD. And at time 0, they will all start to move according to a continuous time random walk on ZD, independently of each other. So once again, you can have more than one particle on each vertex. So how is the aggregate growing? The aggregate is growing according to the following rule. So what is the rule? If you have a particle that is trying to jump into the aggregate, instead of jumping into the aggregate now contains the vertex from which the particle came from. So yeah, once again, if you have a vertex which is not in the aggregate at time t, but it is adjacent to the aggregate, and one particle is trying to jump from V into the aggregate, AT, then now immediately after time t, at time t plus, the aggregate now contains the vertex V from which the particle came from. By the way, if you have more than one particle at V, then they all get absorbed into the aggregate. So absorbed means that they don't move anymore, and they are no longer part of the game. They can't make the aggregate grow again. Okay, I will give an example in a minute, but let me just say that this model is particularly interesting in dimension 1. And why is that? Because in high dimension, it is expected that you don't have a phase transition. So it is expected that for all lambda, for all particle density, the diameter of the aggregate will always go linearly. And in one dimension, you do have a phase transition. So let's talk about the one dimension. So what is going on in the one dimensional model? In here, everything to the right of the origin is completely independent and symmetric to everything to the left of the origin. So we might consider just the model on the positive integers with the aggregate starting from 0. So let's have a simple example. You have Poisson with parameter lambda particles on each one of the vertices, and they start to move according to a continuous time random walk. Yeah, now you have a particle that is trying to jump into the aggregate. Instead of jumping, it freezes and the aggregate grows. Now the aggregate is of size 2. And you keep going like that. Now you have two particles in this vertex next to the aggregate, and one of them tries to jump. So now both of them freeze and the aggregate grows. Now the aggregate is of size 3. And you keep track, you keep going like that. And the only thing you care about is xt, which is the length of the aggregate at time t. And you want to understand the asymptotics of xt as t tends to infinity, and also how does that depend on the density lambda. Yeah, you might expect that as long as lambda is larger, lambda is the expected number of particles on each vertex. As long as lambda is larger, the aggregate will grow faster because you have more particles that can make it grow. Okay, let me tell you about previous results. So there are some results of physicists which I don't know a lot about, but the first rigorous results are due to Kesten and Sidorovicius in the subcritical case. So they have 2 papers where they define this model rigorously and also prove that when lambda is less than 1, the aggregate grows like square root of t. Then it actually follows from a result of Dembo and Tsai that in fact when lambda is less than 1, it concentrates. So you have some constant depending on lambda such that it's equal to c times square root of t plus little of square root of t. What about the supercritical case? So in here, lambda is bigger than 1. It was open for some time. It was conjectured that it should go linearly when lambda is bigger than 1. And indeed, Ellen Sly proved that it does go linearly and also concentrates. I should also mention a result of Sidorovicius and Stauffer, where they considered slightly different model and high dimension. And they proved that for large lambda, the diameter grows linearly. But as I said, it is conjectured that for all lambda, it goes linearly. And actually, it also follows from the result of Sly. So what about the critical case? What do you think? It should be something between, in the subcritical case, it's square root of t, supercritical, it's linear in t. So what happens in the critical case? Yeah, so it was widely believed that in the critical case, it should go like t to the 2/3. And you even have a paper of Sidorovicius and Rath where they give some heuristic arguments for this prediction using PDE theory. And yeah, and you also have an upper bound. So Dembo and Tsai proved an upper bound of t to the 2/3 in the critical case. And the way they did it was by considering they came up with this different model called the frictionless model, which is slightly easier to analyze. And in this model, the aggregate can grow by more than 1 in each step. And they prove that this model grows like t to the 2/3, and you can show that it is stochastically dominates the aggregate. So actually, you get an upper bound of t to the 2/3. Okay, what about what did we prove? So this is the main result. When lambda is equal to 1, indeed, the aggregate grows like t to the 2/3. And we also have a scaling limit. So if you take xt divided by t to the 2/3, it converges to a limiting distribution. And we have the limiting distribution of the entire process. So what did we prove? So you take the aggregate, the size of the aggregate at time s times t, rescale it by t to the 2/3. So now this is a process in S. And as t tends to infinity, it converges to this limiting process in S. Let's try to understand what is this process. So you take an 8/3 dimensional Bessel process starting from 0, raise it to the power minus 2/3, integrate it up to S, and this is your limiting process. By the way, another way of saying it is that the integrand in here satisfies this stochastic differential equation. Dzx equal to 2zx to the 5/2 dbx, where you start from infinity. So how do you understand this? You can think of it as the speed of the process converges to the solution of this equation. Let me show you some simulations. So yeah, this is a simulation that we wrote so you run the process up to time 300,000. And this is the function, the size of the aggregate as a function of time. And this is the subcritical case. So the particle density is 1/2. And the different colors in here, they mean, so these are just independent samples. You just simulate it again and again independently. And yeah, so you see sort of the square root behavior. Square root of 300,000 is roughly 500. So it looks somewhat like that. And you can also see that it is concentrated. So all of these samples look almost the same. What about the supercritical case? So in here, lambda is equal to 1.5, and you can see the linear growth, and also it is also concentrated. So now what about the critical case? So this is a picture from the critical case when lambda is equal to 1. So here it looks less than linear, but much bigger than square root. And you can also see that it is not concentrated. This is something special in the critical case, that it is not concentrated. And what we have is actually the limiting distribution of these random curves that you see in here. So what is the limiting distribution? You take, for example, this bold blue aggregate, and you differentiate it, okay? You differentiate the blue aggregate. And if you believe the theorem, what you see in here is exactly the solution to this equation, this stochastic differential equation that starts from infinity. Okay, yeah, let's talk a little bit about the proof. Are there any questions about this part?
I have a question.
Yes.
So if it starts from infinity at 0, then how does it come down? It has 0 drift. So what makes this? The question is about the scaling limit. So what makes it come down from infinity?
Okay, that's a good question. First of all, let me explain. So you sort of have a trap at 0. So look at this equation. As long as ZT is smaller, the variance is smaller. And you can also see it in this picture, right? And so this process tends to 0 and about starting from infinity. So you can show that if you start from higher and higher places, sort of you have a limit for this sequence of processes. I guess this is how you're supposed to do it rigorously. But yeah, it is well defined when you start from infinity. And as I said, this is like a negative power of a Bessel process that starts from 0. So you can also think about it that way. By the way, actually, this is the fundamental reason why the aggregate grows like t to the 2/3, because it's a nice exercise to show that the solution to this equation, as t tends to infinity, it behaves like t to the -1/3. And then the aggregate, which is the integral of the speed, behaves like t to the 2/3. Okay? Good. So yeah, we want to show that the speed process converges to this equation. So let's talk a little bit about this speed process. Okay, so let ST, this will be the infinitesimal rate of growth of the aggregate at time t, a condition on the past. That is, this is the probability that at a small time interval after t, the aggregate will grow by 1. This should be roughly ST times delta. And you condition on the history of growth of the aggregate, which is the sizes of the aggregate before time t. Okay, what's good about that? That we have a formula for it. So here is the formula. So it turns out that this infinitesimal rate of growth of the aggregate is given exactly by lambda over 2 times the probability that a continuous time random walk. By the way, throughout this talk, WS will be a continuous time random walk that starts from 0. So it's the probability that a continuous time random walk is less than xt minus s, where you condition on these xt, on the sizes of the aggregate before time t. Okay, so let's try to prove this claim.
Can I ask
yes.
question about it? So is it immediate to see that the generator, say, for anything more than +1 is little of delta?
Yes, I mean, the rate function, you can show that it is bounded by constant. It is bounded by lambda over 2, the rate function. So yeah, yes. You're asking whether it can grow by 2 in like a very short period of time.
Just the asymptotics in delta, yes. So it should be little of delta. So for this to be the leading order.
Yes, I think it follows from the proof. Yeah.
Okay, thanks.
Okay, So let's try to prove it. So the only way the aggregate can grow is if you have a particle here right next to the aggregate, which is trying to jump into the aggregate. So the rate of growth has something to do with the number of particles you have right next to the aggregate, at the vertex next to the aggregate, or at xt plus 1. So let's try to think how many particles you have there. So this is the aggregate at time 0, and then it starts to grow, and this is the size of it at time t. And what you care about is how many particles you have here right next to the aggregate, condition on this shape, condition that this is exactly the growth at each time, the size at each time. Okay, so how many particles do you have in here? So you have the particles that started in here, for example, did the random walk and ended up in here. And similarly, and by the way, they always had to be to the right of the aggregate, because if at some point it was to the left of the aggregate, the particle would be absorbed and it wouldn't end up in here. And similarly, you have the particles that started in here and ended up in here, and so on. So now, how many particles do you have that started in here and ended up in here? So in here, initially, you had Poisson lambda particles, and which means that the number of particles that started here and ended up in here is exactly Poisson with parameter lambda times the probability that a continuous time random walk will always be to the right of the aggregate. And similarly from any other point. Now the idea is that you can invert time, you can look at time backward and say that the number of particles in here is exactly Poisson with parameter lambda times the probability that a continuous time random walk will end up wherever, as long as it is always to the right of the aggregate. And you can exactly see it in this equation, right? S is a time parameter that goes backward in time, and you want a probability that it's less than, the WS is less than xt minus s. Okay, so yeah, so we got that the number of particles is exactly Poisson with this parameter. Now, what is the rate? So each particle can either go to the right or to the left. So the rate is exactly half times that. That was easy. Now, actually, there is something wrong with this argument. Did you catch it? Right, so remember here I said that the number of particles initially is Poisson lambda, but it's not true, right? Because we are conditioning on the size of the aggregate. So if the aggregate grew really fast, you probably have more particles in here. But it turns out that this computation that we did using the wrong argument, is actually correct. And the reason for that is a little bit abstract. So this entire thing is actually one giant Poisson process on the space of paths, right? I don't want to get into all the details, but basically the number of particles in here depends on paths that are disjoint from this set. And the history of the aggregate depends on paths that intersect this shape, which means that this is sort of two disjoint sets in this big space of paths. And therefore the Poisson process on each one of them is independent, something like that. If it's not clear, it's not very crucial, but just note, so we kind of prove this claim. So yeah, what's nice about that? You can actually forget about all the individual particles and just sample the entire aggregate using a two-dimensional Poisson process. How are you going to do that? So the size of the aggregate will be all the points. So pi will be a two-dimensional Poisson process. And the size of the aggregate will be all the points under the rate function, S of t, where S of t is given by the formula from before. Yeah, it looks a little bit like a circular definition, right? Xt depends on st and st depends on xt, but it's not, right? St is predictable. It depends on everything to the left of time t of the Poisson process. Yeah, so let me give you a simple example. So, okay, at time t equal to 0, what is this rate function is exactly lambda over 2, right? And then at the beginning, xt is equal to 0, which means that this is 0. So this is just a probability that a continuous time random walk is non-positive up to time t. And you keep going with this curve until you have a point under the curve, and then it jumps, right? And now xt, which is the number of points under the curve, here it's 1 and here it's 0. So here you will have a more complicated. This is the probability that at the beginning the random walk is non-positive, and then it's at most 1. And you keep going like that. So this would be the rate function, and then the number of points would under the curve will be the size of the aggregate. So here the aggregate will be of size 1, 2, 3 at time t. It's clear that it's the same process, right? The rate of growth in this process is exactly s of t dt, like the rate of growth of the aggregate. Okay, so this is the rate function, sort of monotonically decreasing, and then wait until you have a point, and then you jump up. And you have this discontinuity point. Okay, so here is a simple corollary, which might not be so trivial at the beginning. So for all initial particle density, you grow at most linearly and at least like square root of t. Why is that? So we will prove it using a picture. This was the rate function. Now s of t is lambda over 2 times the probability of something. So it is just bounded by lambda over 2. Now the number of particles of the aggregate, the size of the aggregate, which is bounded by the number of particles in this rectangle, which is Poisson with parameter lambda over 2 times t. So it is stochastically dominated by this Poisson, which grows linearly in time. And the lower bound is pretty similar. So this is the probability that the continuous time random walk is bounded by something positive. So it's lower bounded by just the probability that a continuous time random walk is bounded is non-positive, which scales like 1 over root t. So actually, then it is lower bounded by the number of points in this area, and the area grows like root t. Okay, is that clear? Yeah, pretty simple. Okay, so this was sort of an example of a predictable rate function where the point process was the number of points under the rate function. So here is another example of such a process. So you fix the function k from the positive real to the positive reals. Remember this function. And you define the following process. So pi r will be 0 together with all the points under the rate function. And the rate function will just be the sum over the points of the process of this function k at t minus x. So do you recognize this process? What is this process? This is exactly a continuous time branching process, right? So think about it. So pi r would be the set of times. You start from one individual at time 0, and then pi r would be the set of times in which a new individual is born. And then kind of each individual x will give, so y time after it was born, give birth to a new individual with rate k of y. Right, so the rate is the sum over the individuals of the each rate of the rate of it that each individual gives birth. Is that clear? Okay, so anyway, this is a continuous time branching process with offspring distribution, which is Poisson, and the parameter would be the integral of k. I will give maybe a simple example in here. So if you don't have any particles and you just have the particle at time 0, this would be the rate function. And then the number of points you will have here is Poisson with parameter, which is the area, right? So you will have one individual in the first generation. And you keep going like that. So each point you adds another chunk of area, and then the number of points you will have there is Poisson. So you get this branching process. Okay, so here is the main, so this would be the rate function, the sum of all these functions. And does that remind you of something? It looks maybe a little bit like the rate function of the aggregate. So each time it goes down, monotonically decreasing, and then it jumps when you have a new point. So yeah, this is maybe the main idea of this paper, that you can couple the aggregate with such a continuous time branching process. Yeah, how to couple it, just run both of them with the same two-dimensional Poisson process. And yeah, but it's not clear how to make something like that rigorous. And also remember that the branching process depends on this function k. So what is the corresponding function k for the aggregate? And then it turns out that this function k depends on the speed of the aggregate. So this was the speed process. So for each speed, let's say here the speed is roughly alpha or 0.005. So for each alpha, you will couple it with a certain branching process, and then the local noise of the aggregate at each time will be given by the local noise of this continuous time branching process. And there is some computation that you need to do. What is the local noise of the branching process, which depends on alpha, and this will give you the SD. Yeah, so let's talk about the overall strategy in here. You want to prove convergence to the SD. How do you do it? You take this big interval of time, split it to a lot of small intervals of time, and in each small interval of time, you show that conditioned on the history, you get in this little piece of time the right local drift and the right local variance. So this would be the right local, so you take, so ST is the speed, let's say it's roughly alpha, and think of alpha as of order t to the minus 1/3. We need to show that you have the right variance, which is that, and you need to show that the drift term is negligible. So if you bound the drift term by something like that, by the way, t prime would be a point which is slightly bigger than time t. Okay, so you have this small interval of time, t to t prime. Yeah, so if you add up, if you show a bound like that on the drift, and you add up, you get a negligible contribution to the drift, which you don't see in the limit. Good. By the way, so as you see, so it's clear that when the time interval is small, the drift term has a much smaller order than the variance term, or the standard deviation. So actually in here for the variance, the coupling with the branching will be enough, but in order to nail down the exact drift of the aggregate, you will need something else, something much more accurate. Okay, so here is another main idea in here, which is approximating the aggregate by a fixed rate Poisson process. So remember this picture, which is the size of the aggregate at time t, and what you want to understand is this rate of growth, this S of t, which is the probability to miss the aggregate. Now, you might expect that it doesn't really depend here in the beginning of the aggregate, because the probability the random walk will get all the way there and hit here is kind of negligible. So you might expect that the probability to miss the aggregate, maybe it's like missing this tangent line in here. And this indeed would be a first order approximation to this probability. Right, and what would be the slope of this line? It will be exactly the speed of growth, like the recent speed of growth of the aggregate. And instead of approximating to a line, we will just approximate it to a fixed rate Poisson process. Okay, yeah, this is the fixed rate Poisson process, and we say that the probability to miss this one is roughly like the probability to miss the aggregate. Okay, so yeah, this is just saying it again. Instead of computing the probability that the random walk miss the history of the aggregate, let's just compute the probability that it misses a fixed rate Poisson process. So if the speed of the aggregate is roughly alpha, by the way, alpha, you should always think of it from now on as the speed of the aggregate or the recent speed of the aggregate. And yeah, so we will take a fixed rate Poisson process with rate alpha. Good. Okay, let's make this a little bit more rigorous. So you take some alpha, which is very small, and you take a fixed rate Poisson process, pi of alpha. These are these x's, and y of s will be this cumulative function. It will be the process that jumps with rate alpha. You want to compute the probability that a random walk misses this black curve. And so you wanted to condition on the aggregate, on the history of the aggregate. So here you want to condition on this point process, on this fixed rate. Okay, so remember this random variable S, which is the probability lambda over 2 times the probability that a continuous time random walk is bounded by a fixed rate Poisson process. And so this is it. Right now, it has no rigorous connection with the rate of the aggregate, but you should think about it as something analogous to the rate of the aggregate. Another way of writing it is just the probability that tau is equal to infinity, where tau is the stopping time, the first time you hit the black curve. Okay, so here is a simple claim. The expectation of S is, which is just a probability, not conditioning on anything, is given by lambda alpha plus O of alpha squared, where alpha is as alpha tends to 0. And why is that? So this just follows from some standard exponential martingale arguments. I won't give all the details in here because it's pretty standard, but yeah, what you do, you just find the theta such that theta to the power of the Poisson process minus the continuous time random walk is a martingale. Yeah, it's pretty easy to compute it. And yeah, and then you take this martingale and stop it at the stopping time. So this gives you the probability that tau is less than infinity. And actually, what's nice about this exponential martingale argument is that it gives you the Fourier transform of the stopping time, or this exponential moment. So this, it's not important right now, but this was actually pretty important in a more analytic part of this paper, this Fourier, the fact that we have an elementary Fourier transform for the stopping time. Anyway, so yeah, you get that this expectation of the random variable S is roughly lambda alpha plus O of alpha squared. So wait a minute, here we actually understand why lambda equal to 1 is the critical value. Do you see that? So alpha was roughly the speed of growth of the aggregate, and S was analogous to the rate to the new rate of growth. So what do we know here? If you grew at rate roughly alpha, then now the new rate will be lambda alpha. So if lambda is larger than 1, so in the supercritical case, for example, when lambda is larger than 1, if you grew at rate, if your speed was roughly alpha, and alpha becomes too small, then the new rate will be lambda alpha, which means that the process will speed up. So sort of right. So sort of the speed will be bounded away from 0, because if it gets too small, now the new rate will be bigger. And speed bounded away from 0 means that the aggregate grows linearly. And actually, this was the main idea in the argument of Ellen in the supercritical case. And what about the subcritical case? So here it's pretty similar. If lambda is less than 1, you grow at speed alpha. Then the new rate will be lambda alpha, which is less than 1, which means that you will keep slowing down. Now, what happens in the critical case? So here it's not clear, right? So here one might think that it depends on these lower order terms. Yeah, when lambda is equal to 1. But it's not all the story. So this was sort of just a computation of the expectation. So you also need to understand the noise. Okay, so let's talk about the critical case. So from now on, lambda is just equal to 1. And we still want to forget about the aggregate and just work with the fixed rate Poisson process. So remember, you want to understand this random variable S, which is the probability to miss the aggregate, which is the probability to miss the Poisson process, conditioned on the Poisson process. And so it used to be lambda over 2, but now lambda is equal to 1. And we computed that the expectation is roughly alpha. Okay, now you have the following theorem. We call this maybe the approximation theorem. So the idea here is to get better and better approximation of this random variable S. Okay, so if you want an approximation which doesn't depend on the Poisson process at all, just take the expectation of S. And it turns out that this would be a pretty good approximation of order alpha to the 3/2. Now, if you want another approximation, which is slightly better, that depends a little bit on the Poisson process, it turns out you can get an approximation of order alpha squared. And this S1, what this S1 exactly is sort of a sum over the individual contributions of each one of the points of the Poisson process. Turns out you can write a good approximation that depends on that you can write as a sum of the individual contribution of each point. So each point, each jump point adds a little bit to the overall probability to miss this curve. But this would not be enough. So you need the second order approximation, and what is that? This will be something that depends on the correlation of the points. Yeah, so you had one approximation which doesn't depend on the process at all, second one which depends on the individual contribution of each jump point, and the third one which takes into account correlation. So it sort of subtracts the correlation between pairs of points. And you can actually keep going like that, I think, each time improving by a factor of square root of alpha, and then you can subtract the correlation between three pairs of points and so on. But luckily, this is enough. The second order approximation would be enough. Actually, in order to prove that it's enough, you need to bound the correlation between three pairs of points, but you can do it. Anyway, yeah, so forget about, okay, let's understand this complicated formula. So integrating with respect to d pi alpha is the point process, just means sum over the points of the point process. So here you have a double sum over the points of the process. So it's just like summing over pairs of points. Just think about this as the contribution of each pair of points. Okay, but let's concentrate for a second on this first order approximation. So, okay, remember this picture of the aggregate growing in time? We want to understand this rate of growth, which has something to do with the probability that you miss the history of the aggregate. And similarly, you have here the fixed rate Poisson process. Now, if you believe that this point process, the fixed rate process, is sufficiently close to this point process, this is the point process that you have, this is the set of times in which the aggregate grew. Yeah, so you might expect that the same formula that you have here, you will also have here, but when you go backward in time, right? This process actually goes backward in time. And so you have that the rate of the aggregate is roughly this given by the sum. And do you recognize that? So what is a process that is growing with this kind of rate? It's exactly a branching process from before. Yeah, so this sort of make it rigorous, the approximation to the branching process. So yeah, it turns out the rate of the aggregate is roughly like a rate of a continuous time branching process. And by the way, the function k from the theorem, it will be something to do with the fixed rate process. So tau will be the stopping time from the fixed rate process. Yeah, by the way, so you can see that this function depends on alpha, as I said. So for each speed alpha, you will couple it with a slightly different branching process. And one more important thing to say is that this function, not very hard to show that it integrates to 1. So actually, this is a critical branching process. So you couple the critical aggregate with a critical branching process. Good. Yeah, so let me say something about the proof of this theorem. I won't have time to really prove it, but the idea here is to do, so this is just the fixed rate. The idea here, you have this random variable S, you understand its expectation. What you do is you do the Doob martingale of this random variable. You need to condition on the entire black curve in here. So you start exposing the curve from left to right, start exposing this Poisson process from left to right, and you do the analysis of this Doob martingale, try to do try to compute the infinitesimal increment of this martingale and compute the contribution of each individual jump. Yeah, this was a little bit vague, but you can do it to get this increasingly better and better approximations. And then you need to use a lot of martingale concentrations. By the way, okay, let me tell you one more thing about about this part, so here we said that if this point process is sufficiently close to the point process of the aggregate growth times, then you get the same formula. But how to make this rigorous? So what do I mean that this point process is like this point process? So here there is a nice argument. It's a density argument. So here this point process is actually absolutely continuous with respect to this point process. And you can bound for a certain, if you take alpha, which is close to the speed of growth of the aggregate, it turns out that you can bound this density by some e to some power of log. And since these approximations, we got them using martingale concentration, they actually holds with exponentially high probability. And so everything, since the density is bounded by e to some power of log, anything that holds with exponentially high probability in the fixed rate also holds in the aggregate. So this was sort of the idea. Okay, good. Yeah, I guess I will skip the proof of this theorem. Yeah, okay, but so now let's just work with the branching formula. We want to compute the local noise. So we want to compute the variance of this continuous time branching process. Yeah, so that's what's nice about this branching, that you can actually compute things. For example, you can compute what is the expected contribution of a particle at time s and all of its offsprings to the rate at time t. So you're adding another particle here at time s, and you are asking what is the expected rate at time t, where the rate is given by this sum. By the way, dx means just the jump points of the aggregate, the set of points in which the aggregate grow. Okay, so I claim that it's given by the following sum. What is that? So first of all, this is the contribution of the particle of itself to this sum, right? So it contributes k of t minus s. Now, this is the contribution of the first generation of the branching process, right? What is the expected number of particles you have in the first generation? It's 1. And then how much each particle is going to contribute to this rate? K of t minus x. And then the probability that it falls in x is exactly k of x minus s. Anyway, yeah, and this is the contribution from the second generation and so on. So what did we get in here? This kind of infinite sum of convolution or a density of a renewal process. And yes, so this is the contribution. This is the expected contribution of a particle at time s to the rate at time t. And now, let's say t is very far away from s. So what is the contribution? It's given by the asymptotics of this renewal of this density of a renewal process, right? The sum of convolution is kind of the density of the renewal process. And you can compute this, right? Because the density of a renewal process is just 1 over the expectation. So you can show that actually as t tends to infinity, this renewal function behaves like 2 alpha squared. And this 2 is actually the 2 from the SD. Do you see that? So each particle at time s contributes roughly 2 alpha squared to the rate at time t. So kind of the rate at time t is a sum of independent random variables, each one of size 2 alpha squared. So yeah, I guess the way to make this rigorous is to consider the Doob martingale of s of t, of the rate at time t, and to start exposing it and to understand what is the contribution of each individual particle at time s. This should be roughly 2 alpha squared times the indicator that you have a point in this little interval between s and s plus delta. And then it's a martingale, so you need to subtract the probability that you have a point. And it's roughly a fixed rate alpha, roughly a Poisson process with fixed rate alpha. So it's alpha times delta. Yeah, I guess this is a little bit vague. But anyway, this sort of justifies that s of t is a sum of independent random variables. So what is the variance now? It's d squared times the probability of the Bernoulli times the number of variables. So you get here exactly what you wanted to prove, that the local variance, just computed the local variance of the branching process. Okay, let me say one more word about the drift term. So as I said, in order to nail down the local drift, you need to consider the second order approximation, which is this more complicated formula. And so this is a very complicated process, but luckily we just need the expectation of that, which is the drift term. And not hard to show that this expectation of this complicated random integral is given by this even more complicated deterministic integral, which has something to do with this density, this renewal function, and also with the function j. But anyway, we were stuck for a long time on trying to estimate this integral, maybe a few months. And then we found this math overflow question of Yuval Filmus from the Technion, if you know him, about renewal process. And the methods in this question allowed us to estimate this integral. If I'll have time, I will say something about this question. But anyway, you can estimate this integral, this expectation to be roughly 2 alpha squared, which exactly cancels this part. So this sort of tells you that the local drift is 0. So you don't get a drift term to the SD. Okay, good. I have maybe 3 more minutes to tell you about this question, about renewal process. It's kind of, so from now on, it's completely independent of everything. Yeah, so you have this renewal process, you have uniform random variables, and you consider this renewal process, which is the number of events before time t. And what do we know? We know that from renewal theory that it behaves like the time over the expectation of u, plus some O of square root of t from maybe central limit theorem. And the expectation of uniform is half, so you get here 2t. Now, okay, this is the random variable, but what about if we just want the expectation of it? So what is the size of the expectation minus 2t? Yeah, so here is a claim. It's equal to 2t plus 2/3 plus some exponentially small error. And how do you do that? So you can write this expectation as the sum of the probabilities that you are larger than n, which is exactly the probability that the sum of uniform is bounded by t. Now you do this Fourier thing. You have the characteristic function of the uniform. So the characteristic function of the sum, or maybe the Laplace transform of the sum, is just the Laplace transform to the power n. And you need to sum it over n. So you get a geometric series, and you get this integral when you sum up the geometric series. Now you can compute, you can substitute the characteristic, the Laplace transform of a uniform random variable, and you get this simple integral. So you can represent the expectation of the renewal process as a simple integral. Okay, where you need to integrate over a line like that. Now you want to take this line and push it as much to the left as possible. And why is that? Because what is the absolute value of this function? It's e to the t times real part of s. So as long as real part of s is smaller, you get a smaller integral. So this function has one pole at 0, or a pole of order 3 at 0. And it has some other poles that have something to do with the 0, which are exactly the zeros of this function. So you take this, push it to the left, compute the residue in here, which will give you the main term. And then you want to bound the integral over this part, which is e to the t times real part of s. So it's exponentially small when s is negative. Yeah, so here, so you get this claim, but maybe a bit mysteriously, this exact rate of exponential decay is given by the rightmost 0 of this function, by the real part of the rightmost 0 of this function. But yeah, anyway, we can do the same in our situation. You remember this computation with the exponential martingale from before? So we actually got a simple formula for the Fourier transform of the stopping time, which is related to the Fourier transform of this function k. And then we have this renewal process, which we care about, and you can write it as such an integral similarly. So yeah, here we don't really have these simple poles, but we have a more complicated line singularity of a square root. So it turns out what you need to do in here is compute the residue in here, which will give you the main term, and then consider some kind of a Hankel loop like that with a certain particular distance from this line singularity. And yeah, I won't give a lot of details, but this is the kind of things that we did. So this kind of methods allowed us to estimate, to get some important estimates on this renewal function, and also estimate the double integral, the complicated double integral from the drift term. And so this gave us the local drift of the aggregate. Yeah, I guess I will finish here. Yeah. Yeah, there is some nice conjecture in here. What happens when you start with a different law? So here we started with Poisson number of particles on each vertex, and now you can start with any other distribution. And yeah, so the conjecture is that you will get a Bessel process with a different dimension, and then you can do so the dimension will depend on the variance of the distribution. Yeah, I guess I will finish here. Yeah, thank you. Questions?
Thank you, Dor. So questions for Dor?
So did you think about a continuous version of this process? So for instance, starting with hard disks, and say the center of the disk is a Poisson point process on R, and so your rule was when one particle chooses to jump on the aggregate, then you essentially kill all the rest. So you will need to do some breaking rule, like you kill all of the disks that intersect the disks that just touch your aggregate, something like this. But other than this, it seems like your arguments should work for just continuous branching processes, etc.
We haven't considered it. There are some other continuous version of it which has something to do with PDE. I think it is related to the Stefan problem from PDE, but I really don't know a lot about it.
But in your model, instead of this rule that you wait until a particle jumps to your aggregate and then you add it and kill all the rest, if you just wait until, I mean, whenever a particle hits the boundary of distance 1 from your aggregate, you add it, but then you might need to add a cluster, not just one, because instantaneously you might have a, so do you lose the phase transition?
Yeah, it's an interesting model, and I really have no idea. Yeah.
Okay. Thanks.
Dor, very nice work. So regarding this open problem, so if the initial distribution is not Poisson, then you lose the connection to the random walk that you had, that the speed process is the probability of a random walk given the past.
Yeah, yes. First of all, so here we had the property that everything is Poisson. The entire thing is Poisson. So we had some nice formulas. If you have different distribution, you might try to approximate it to a Poisson and maybe use the same arguments. So here maybe it's a little bit surprising that you get a different behavior, because if you forget about the aggregate and you just let the random walk, yeah, then it becomes pretty close to Poisson after some time, right? No matter what is the initial distribution. But it turns out that it is not approaching Poisson fast enough, and the aggregate in the critical case grows faster than the time it takes for it to become Poisson. So you get this different limiting shape. But yeah, it is still considered. Yeah, I'm sorry.
The non-critical cases are solved then?
I guess you could. Yeah, I think we can solve. We don't. I think it shouldn't be very hard.
Good. And I had a question about something you said in the very beginning. So you said that in higher dimensions, you expect that there is no phase transition. But let me just ask about the shape of the aggregate. So is it that if the density lambda is very large, then it actually fits the ball? And if the density is not that large, maybe it's very small, in fact, then it still has linear diameter, but it has a lot of gaps, and that's how it reaches this huge diameter? Because it
right. So I think that Ellen told me about this once. In order to prove that it grows linearly in any for any initial density, you need to first show something about the regular DLA to show that it is not space filling. But it's actually an open problem to show, and probably maybe hard to show that the regular DLA is not space filling. Yeah, and I don't know about the limiting shape and the ball and.
All right. Okay, thanks.
Thank you.
Okay, so thank you, Dor, and I guess we see you next week on the usual time.
Maybe we stop the recording and I